Hello, class. Okay, so we're going to begin talking about this subject called thermodynamics, which is about the flow of heat. And we're going to begin by talking about temperature. So we have a very kind of intuitive idea. We use the word temperature in everyday language, but we want to find, what temperature actually means. And let's say we have two objects, so A and B, that are in thermal contact with each other. So what thermal contact means is that they can exchange energy. So they can be touching each other. That'd be one way to do it. But even if they're not touching each other, they can still exchange energy. An example of that would be the Earth and the Sun. We receive energy from the Sun. And so if these two objects are in thermal contact, we might notice that energy will spontaneously flow from one object to the other. So let's say we put these objects in contact, and we notice that energy flows from object A to object B. And it just does that automatically, and there's no other reason for this energy to flow. Not like, say, A is moving and it collides with B and transfers energy that way. It's a spontaneous flow of energy. And we can say that object A is at a higher temperature than object B. And so by doing that, we have a way of kind of ordering objects by just by observing this flow of energy. And so like say we have A and B, where energy flows from A to B spontaneously. And say we have object C. And if B and C are in contact, energy flows from B to C. It gives an order. We say A is the hottest object, and then B is the next hottest, and C is the least hot out of these three objects. Now, we want to do better than that, though. We want to actually be able to assign a numerical value to what temperature is. And we're going to, right now, have kind of an operational way to define a temperature scale. So we're going to give a way to measure it without really defining what temperature is, but give us a way to assign numerical values to it. And we can do that with a thermometer. So say we have a thermometer. If you look at an old-fashioned thermometer, you've got this tube filled with mercury, or partially filled with mercury. So we have this bulb at the end to contain extra mercury. And the idea, which is something we're going to talk about later, is we know that when we heat things, they tend to expand. At least in certain temperature ranges, that always occurs. And so if we heat the mercury is going to expand, and we can come up with a numerical scale. So we're going to talk about two scales that are in kind of common use. The first one that was ever defined, I believe, was the Fahrenheit scale. This was named after a guy named Fahrenheit, and he was the first one that could actually make thermometers that agreed with each other. So you could make two thermometers and they both read the same temperature. That was a big, kind of a big deal at the time. And what Fahrenheit did is he selected two reference points. He said body temperature, just the human body temperature. He assigned a value of 100 degrees. And for the other reference point, he used this mixture of ice water and ammonia. Or, so I know there's ice water and salt. There might have been ammonia too, I don't remember. But he basically found the coldest substance that he could and said that's going to be assigned a value of 0. And so to define a temperature scale, you need these two reference points. You need something you're going to call, well, you give a value. You can say 0 and 100, for example. And then for an operational way to measure temperature, you can design a thermometer. So say we have this thermometer and we place it in this ice water mixed with salt. And the mercury is going to be rather cold. And so it's the volume of this mercury is going to decrease. And we can just mark off right here wherever it comes into what we call thermal equilibrium. So let me erase object C here. Say we just have objects A and B. And energy is going to flow from object A to B whenever they're in thermal contact. And so we say A is at a higher temperature than B. However, when energy flows from A to B, A is losing energy and B is gaining energy. So A is going to cool off. And B is going to heat up. And so what happens is the temperature of A is going down, temperature of B is going up. And the greater the difference in temperature, the faster the energy is going to flow from one to the other. And as they get closer, the rate's going to slow down, and eventually they will reach the same temperature. And when that happens, there's no more flow of energy, and so they are at the same temperature. Okay, so so you put the thermometer in this mixture of ice, water, and salt that Fahrenheit defined. And then you have to wait until this thermometer reaches thermal equilibrium with this mixture of ice water. And then we can mark down on our thermometer 0. And then we say, do what you do with these old-fashioned thermometers. You measure your body temperature with it. You put it in your mouth and just let it come into thermal equilibrium with your body, which Fahrenheit defined to be 100 degrees. So the mercury level is going to rise, and then we mark down 100 at that temperature when we're in thermal equilibrium with the human body. Now, this is, of course, a very bad reference point because it depends on biology. Different people have different temperatures, and so not a very good reference point, but apparently that's what Fahrenheit used. And the idea behind how a thermometer works is we just we assume that the expansion is linear. We're going to talk more about thermal expansion later, how when you heat things up, they expand. But the expansion is basically linear. So let's say that we place this thermometer in contact with another object, and the mercury level rises, say here. What we can do with our thermometers, let's say we break this up from 0 to 100, say we put like 100 tick marks here, and just mark off the temperature in 1 degree increments, then we can just read, if that's like, say, 55% of the way from 0 to 100, that's a temperature of 55 degrees. So once you have your two reference level, you can just mark off equally spaced lines in between. And like in this case, if you have 100 tick marks, each one would be 1 degree. And so this is a way that we can actually assign numerical values to temperature. We never really defined what temperature is. It turns out it's kind of a difficult thing to define in practice. We'll talk a little bit about that later, but yeah, we basically define it by what our thermometer reads. Now, there's a fundamental assumption here, something called the Zeroth Law of Thermodynamics. So the subject, thermodynamics, it's governed by laws, and historically, thermodynamics was worked out, mostly I think, a lot of it in the 1800s. And so it was after Newton, but before the atomic theory of matter. And so we have these laws of thermodynamics. We actually have 4 of them. And, well, there's like the first law of thermodynamics, second law, third law, and then the zeroth law. I think that was kind of, historically, they probably realized this was logically necessary after they had already named the other ones. But yeah, so we start with the zeroth law. Or we'll just call it the zeroth law. And what this says is, we talked about this idea of thermal equilibrium, where when you bring 2 objects together so they can exchange energy, and if you wait long enough, if one is hotter than the other, energy is going to flow from the hot object to the cold object. That'll cool off the hotter object and heat up the cooler object, and so the temperatures are going to get closer and closer together. Once the temperatures are equal, there's going to be no further exchange of energy. So energy is going to keep on flowing until they reach the same temperature. So this zeroth law of thermodynamics, basically what this says is, say that A and B are in thermal equilibrium. Okay, so you have 2 objects, A and B, that are in thermal equilibrium. And let's say A and C are also in thermal equilibrium. So what the zeroth law of thermodynamics tells us is that this implies that B and C are in thermal equilibrium. Now, when objects are in thermal equilibrium, they're at the same temperature. And so it might seem like this is completely trivial and obvious. Another way of saying, like, say A and B are both 55 degrees, and A and C are both 55 degrees, then B and C are both 55 degrees. It seems incredibly obvious and, like, not even worth mentioning. But it is logically necessary because we're using this idea of, like, energy flowing to define, this basic idea of temperature in the first place. And it's theoretically, it's possible, at least logically speaking, that, if A and B are in thermal equilibrium, maybe there's other factors than temperature involved. Like maybe the density of the objects could have some effect on, say energy flows from A to B, for example, and then eventually energy will stop flowing. And maybe that it doesn't only depend on temperature. Maybe if density was a factor, then A and B could be in thermal equilibrium. But then, say A and C are in thermal equilibrium as well. But then if you put B and C together, energy is going to flow spontaneously between these 2 objects because of other differences. So what the Zero Law of Thermodynamics is saying is that the only thing that determines this spontaneous flow of energy is temperature. And yeah, so this is kind of, we can take this kind of like a postulate. We can just accept this fact. These kind of play the role that Newton's laws play in mechanics. We've got these laws. Newton came up with them for a good reason. And so we kind of just treat them as postulates once we discover them and determine that they work. They form the foundation of the subject. And thermodynamics was developed in the 1800s. And so it kind of developed along the same lines. We have these postulates, which are the foundation of the subject. But nowadays, once the atomic theory of matter came around, that kind of changed how we can deal with this. Some of the same problems we can deal with in a different way, like a more fundamental way. Like we're going to see later on, we're going to talk about the first law of thermodynamics. That comes next. And really, all the first law of thermodynamics is conservation of energy, which is something we know about anyways. But again, when they developed these laws of thermodynamics, they didn't really understand what heat was. Like what temperature actually are. So we're kind of going back to an 18th century approach when we're looking at this topic. Okay, so we've got the Fahrenheit scale, which is what we use here in America. There's another scale which is used in the rest of the world. This is the Celsius scale. So this was named after a guy named Celsius. This is the second major temperature scale that was developed. And this was important because this is more closely related to our SI system of units. It's not what we use in the SI system, but it's close to it. So in the Celsius scale, again, we have two reference levels. Well, what Celsius used is just water. So he used ice water, just ordinary ice water, not with like salt added to it. So say you have like distilled water, you remove everything from it except for the water, mix it with ice, and we'll call that 0 degrees Celsius. Just write the number 0. And then if we have boiling water, that's 100 degrees Celsius. Now, in a sense, this is an improvement over the Fahrenheit scale because, relying on body temperature, not a very good idea. I mean, if you ask people what's the average human body temperature, everyone says 98.6 degrees, but again, it depends on the person. I suspect that Fahrenheit called it 100, it was... Maybe his thermometers weren't as accurate as what we have now. So what he called 100, now we call 98.6, which would be the average around a lot of people. But, yeah, switching to water is certainly an improvement. It's not a perfect system, though, because in practice, it can be fairly difficult to work with. We'd have to use pure water. We'd have to distill it, get rid of all the normal minerals that are typically found in water. And another factor that's very important is pressure. Like you notice, or I don't know if you have noticed this, but like say you moved to Colorado and you wanted to cook spaghetti there, it would take longer. And the reason why is Colorado is at a higher altitude. You're living in the mountains, and the atmospheric pressure is lower, which means water boils at a lower temperature up in, at a higher altitude. So if the pressure is lower, the water boils at a lower temperature. And so you need to specify normal atmospheric conditions. So this would have to take case at a particular atmospheric pressure. And then we would define things the same way as before. So we have our two reference levels. We could make a thermometer, put it in a mixture of ice water, mark that as 0, and boiling water, mark that as 100, and then we have a thermometer calibrated to our Celsius temperature scale. Okay. Now that we have these two different temperature scales that are in common use, we have to be able to convert between them. So we have to be able to go from, say, Celsius to Fahrenheit or Fahrenheit to Celsius. And we're going to do this in two different ways. One is kind of a graphical approach. We'll start with that. And we'll do this by just picking a number. We'll convert one to another. So let's say we want to convert 35 degrees Celsius to Fahrenheit. So what I mean by a graphical approach is, I'll draw a picture here. Let's say this is Celsius. Here's our Fahrenheit scale. And we're going to say these two reference lines are for water. This is the freezing point, the ice water. And this is the boiling point. So this is what Celsius used. And these values are 0 and 100. Now, the Fahrenheit scale was based on different reference levels, but again, Fahrenheit used human body temperature, and the reason he used that mixture of ice water with these things added to it is that was the coldest thing he could come up with. And apparently he thought no one would ever be able to find anything colder than that, which of course is not true. And so basically what we've done is kind of redefine the Fahrenheit scale to base it on the freezing and boiling point of water. And so water freezes at 32 degrees Fahrenheit and it boils at 212 degrees Fahrenheit. Okay, so we want to convert, say, 35 degrees Celsius to Fahrenheit. So from 0 to 100, we go about here. This is our temperature. This is 35 degrees. So what does that correspond to over here? We want to find that next, that point there. And so what we're going to do is let's look at the difference between the freezing and the boiling point. So that's a difference of 100 degrees on the Celsius scale. On the Fahrenheit scale, that's a difference of 180 degrees. And so we can set this equation here. We can say that 100 Celsius degrees equals 180 Fahrenheit degrees. Now, we have to be a little careful by what this equation means. Because what we're talking about here is differences in temperatures. We're talking about the difference between the freezing and the boiling point. So that's 100 degrees on the Celsius scale. 212 minus 32 is 180. So that'd be 180 on the Fahrenheit scale. And this equation that I wrote down is fine as long as you understand we are talking about changes in temperature. Not a temperature reading. Like if you ask what the temperature is outside, you might say it's 80 degrees Fahrenheit, We're just talking about a single number here, and this equation would not apply if we're talking about individual temperatures. And the reason why is because there's this offset between the two scales. They're zero, like the zero on the Fahrenheit scale is down here somewhere. And so it's clearly the case that 100 degrees Celsius is not the same as 180 degrees Fahrenheit. 100 degrees Celsius is 212 degrees Fahrenheit. So as long as you understand that this applies when we're talking about changes in temperature, that equation is fine. And a very common convention, just so you don't ever get mixed up about this, if you want to know the reading, like a temperature reading, like right now, say the temperature is 80 degrees Fahrenheit, you could write it like this, 80 degrees Fahrenheit. Now, let's say tonight it's going to drop down to 50 degrees Fahrenheit. So we can say the change in temperature, well, I guess it's negative because it's going from 80 to 50. So we drop 30 degrees, and to signify that we're talking about a change, we'd say it a little differently. For a reading, we say like 80 degrees Fahrenheit, but if we're talking about a change, then we'd say like minus 30 Fahrenheit degrees. Just so we don't get mixed up on this kind of annoying issue that we have this offset in these scales. So, yeah, this is a nice conversion factor between these two temperature scales. And there's a common factor of 20. So if we divide each by 20, we can say 5 Celsius degrees is equal to 9 Fahrenheit degrees. 100 divided by 20 is 5. 180 over 20 is 9. Okay. So now, if we look at this change here, we're going from 0 to 35 degrees. So delta T, we call that our change. Like if we imagine starting from the freezing point, this is 35 Celsius degrees. And now let's convert that to Fahrenheit degrees. So we have 9 Fahrenheit degrees over 5 Celsius degrees, using that conversion factor. We're just multiplying by 1. 9 Fahrenheit degrees is equal to 5 Celsius degrees. So we're just multiplying by 1. We're not changing anything. 35 over 5 is 7 times 9. That would be 63 Fahrenheit degrees. Now that is the change in temperature from the freezing point. So to get the temperature in Fahrenheit, we have to recognize we're starting from the freezing point and then we're adding 63 degrees. So we start at 32 and then add 63. So this would be 95 degrees. So 35 degrees Celsius equal 95 degrees Fahrenheit. So this is a graphical way of doing things. You can draw a picture, and I kind of like this approach because you can kind of see if you get some kind of nonsense number, it'll usually kind of be obvious that I'll finish this picture. We got a 35 here, and that was 63. So like the same change on one scale is 35 degrees, on the other it's 63. And then we can use that to find our final temperature. Now if we wanted to do the other way, like go from Fahrenheit to Celsius, let's just keep the same picture. Let's say we want 95 degrees Fahrenheit and convert it to Celsius. We just do all these steps basically. We'd find the difference between 95 and 32, which is 63. And then we'd convert that to Celsius and get 35. And then since we're starting from 0, we'd end up at 35 degrees Celsius. So you can go from either direction, from Celsius to Fahrenheit, Fahrenheit to Celsius. It's kind of a nice way of doing it. So that's a graphical approach. Now I want to look at another approach. We can come up with an equation that's just going to convert back and forth between them. So let's do that next. And again, let's start by converting. Let's find a formula that's going to convert from Celsius to Fahrenheit. So we're going to say our temperature on the Celsius scale, we're going to call that Tc. And the temperature on the Fahrenheit scale is Tf. So we're going to convert from Celsius to Fahrenheit. So we know the temperature in degrees Celsius. So what we're looking for is Tf equals something that involves Tc. We know the temperature in Celsius, so we plug that into the right side and it gives us the left side. Now remember, our temperature scales are linear. We had a thermometer, we broke it up into like 100 equally spaced degree marks between 0 and 100. Like each change is the same, it's a linear scale. So we have a linear equation that describes the conversion between them has to be linear. So again, we know Celsius, we plug it in, and that gives us the temperature on the Fahrenheit scale. Now, we don't know what A and B are. We have to figure those out. But we know a few things though. We know that 0 degrees Celsius is equal to 32 degrees Fahrenheit. And we know that 100 degrees Celsius is equal to 212 degrees Fahrenheit. And so let's plug both of these in. Let's start by plugging in the first one. So we plug in 0 on the Celsius scale and we get 32 on the Fahrenheit scale. So we know that 32 is equal to A times 0 plus B. And then if we plug in the other one, we know 212 degrees Fahrenheit is equal to 100 degrees Celsius. So we have these two equations with two unknowns. Our unknowns are A and B. So we want to find those. And it turns out this is a very easy system of equations to solve. Right off the bat, this A cancels out, and we can see that B is equal to 32. And now if we plug that in, we have 212 equals 100A plus 32. If we subtract 32, 180 equals 100A. This ratio might seem familiar. Remember, 180 on the Fahrenheit scale is 100 on the Celsius scale. So if we divide by 100, let's divide by 5, or 20 actually. So we get 9 equals 5A, or A is equal to 9 over 5. And so now we have our formula. I'll write that down. I'll write over here. We have TF. That's equal to A, so that'll be 9/5 TC plus B, which is 32. And of course, this has the advantage of just being very convenient. It's a formula. You know one, you plug it in and get the other. If you have the temperature in Fahrenheit and you want to know temperature in the Celsius scale, well, it's easy enough to solve. So you only really need one equation to convert between these two scales. Okay, so what we've done is we gave this this idea of temperature that, when objects can spontaneously exchange energy just by being in thermal contact with each other, energy always flows one way. It flows from like one object to the other. And we say that the object that is losing energy is the hotter object, and the one that's gaining energy is the colder object. So we have this idea of how we can order things in terms of like how hot they are. Like if one object on this scale, if we just have like hot and cold, we could have A, B, C, D, whatever, where like C is the hottest, D is the coldest. If we bring any of these two in contact, we can immediately tell which way energy is going to flow. Like if we bring A and D together, energy is going to flow from A to D. B and D, like basically any object in contact with D, energy is going to flow into D. If we bring, say, A and C together, energy is going to flow from C to A. So it gives us a way to just organize how hot they are relative to each other. And then we have this kind of operational procedure for defining a number associated with temperature. And then we can kind of redefine it and say that, energy flows from the object at a higher temperature to the object at a lower temperature. And we define two types of scales, Fahrenheit and Celsius. And finally, we discuss two methods to convert between these two scales. And I think this will be a good place to stop. What we're going to talk about next, we're going to talk about another type of thermometer. And that's going to lead to a very important result, which will ultimately lead to another temperature scale. But I think we'll do that in a separate video to keep this video from being too long. So that'll be it for this one.